All right, class. Good evening. Am I audible to all of you? Atif, Fatima, Hamza,
Yes, teacher.
Hiba, Kulsum, Sara, and Sam. All right. So in the last class, we had completed motional EMF, no, and we had done lens law. All the questions also we had completed. Fine. Now see, before starting with the induction, you have a very small topic that is eddy currents. See, eddy currents is not now included in your paper. Otherwise, eddy currents question used to come in the subjective papers. What are eddy currents? Give some experiments to prove eddy current. Just a second. All these used to come. So now what you have to do, you just have to just go through it once. What are eddy currents for your knowledge? I'll tell you what are eddy currents. But remember, these are not included for your board exam. Now, in case of eddy current, EMF we have studied, currents we have studied, and we have also studied whenever there is whenever there is a change in magnetic flux, whenever magnetic flux linked with the coil changes. So what happens whenever magnetic flux linked with the coil changes? EMF was induced. EMF was induced, current was also induced. So similarly, we had eddy currents. Eddy current was just a name. See, currents can be induced, but not only in just the conducting coils that you have studied. Conducting coils you have studied, but also they were able to induce EMF in sheets or blocks. All right, so currents can be induced in sheets and blocks as well. And now what happened whenever the magnetic flux linked with a sheet or a block got changed? Whenever this changed, there was a change in the magnetic flux, whether it increased or decreased, whatever happened with it. So whenever magnetic flux changes, what happened? EMF got induced. Now, whenever this EMF was induced, the induced current flow in closed path in planes perpendicular to the lines of force. So these currents now look like whirlpools. If this was a south bar magnet, this was the polarity of a north magnet, and we keep a sheet within it. So eddy currents now flow like this. They are circular in the form of whirlpool. Like this, these are the eddy currents. So whirlpool means what? Whirlpools are also called as eddies. So based on this, the name was given as eddy current. There was one more name class. These eddy currents were also known as Foucault currents. There was a scientist named Foucault. I don't remember the complete name of the scientist, but he was the one to firstly discover the eddy currents, and eddy currents was that's because of his name. Eddy currents were also known as Foucault current. So eddy currents are what? Eddy currents are basically currents which are induced in the metallic masses like the blocks or sheets whenever magnetic flux, there's a change in the magnetic flux through them. And they also oppose the change in magnetic flux. So their direction can be given by Lenz law. So this is the basic that you should remember. And one or two things that you should remember is regarding their application. So eddy currents are used in the induction furnace. They are used in the induction furnace. So what happened was, if whenever a metal specimen that was kept in rapidly changing magnetic field, so large eddy currents could be produced. Similarly, there was a concept, I don't know if you people have, electromagnetic damping. Electromagnetic damping. So whenever a current was passed through a galvanometer, the coil suffers few oscillations before coming to rest in the final position. So as the coil moves in magnetic field, induced current is set in the coil, that oppose the motion of it. So it opposed the motion and the oscillations that occurred. They were damped. In class 11th, you must have done oscillation, damping and undamping. So damped oscillations are what? These are electromagnetic damping comes under this damped oscillations. Damped, undamped oscillation you must have studied, no? When the amplitude decreases or when the amplitude remains constant, by this you can. So here also eddy current gets involved. Then you have electric brakes. And one more you can write it, the concept of speedometers. In case of electric brakes, what happens? Strong magnetic field is applied to the rotating drum attached to the wheel. So eddy currents are set up in the drum which exert a torque on the drum. So then the train or your vehicle stops. In case of speedometer also, magnet rotates with the speed of the vehicle. So as the magnet rotates, then the eddy currents are generated. So these are just for your knowledge. This question does not come in the exam. Just keep in mind, and we'll start with the main topic, that is induction. First, note out these points. Done, class? Let's start with induction. Now, induction comes. Induction comes a lot in the exam. So basically, there are two types of induction. Self-induction is there, and mutual induction is there. Self-induction, let's start with self-induction. Induction word means inducing only. Inducing EMF, inducing current. So that is known as induction. The process of inducing current or inducing EMF, that is known as induction. So this is also self-induction, and it is one is mutual induction. In case of self-induction, see what is meant by self-induction. So when a current flows in a coil, it gives rise to magnetic flux through the coil. Now, as the strength of current changes, let's say it increases or it decreases, what happens? The link magnetic flux also changes. There's a change in the magnetic flux also. And this gives an opposing EMF. So what has happened? An EMF has been induced because of the change in the current. So this EMF that has been induced, this is known as back EMF. This is known as back EMF, or there is one more name which is known as self-induced EMF. Back EMF or self-induced EMF. So what happened? EMF got induced because of the change in current that occurred. So because of the change in current, EMF got induced. So this phenomena is known as self-induction, because in the same coil only current is changing, flux is changing, and EMF is getting induced. No other coil is required. In mutual induction, you will see presence of more than a single coil. So in this, what is happening? A single coil is there, current is changing, flux is getting changed, and there is generation of EMF. Now, what is, let me write down the proper definition of it. So self-induction, this is what? It's the phenomena of production of induced EMF. Of production of induced EMF. Now, when a changing current passes through, so this is the definition, when a changing current passes through. So whenever current got changed, flux got changed, and because of this EMF was induced. So this whole phenomena from the change in current to the production of EMF is known as self-induction. Now, change in current is there means what? Current is increasing, so flux will increase. Let's say current decrease, so flux will decrease, but there will be an induced EMF. And this is happening on a single coil only. Let's say this is a single coil, so current is getting increased in this coil. Flux is getting increased in this coil only. So what will happen? Ultimately, EMF will be induced in this only. That's why we call it as self-induction. Now, in just there's an experiment to support this, or this rarely comes in exam, but in your answers you can add on it if the answer is of a more score. What happens to the coil if switching key is means your switch is a closing switch or an opening switch? So see, first case, let's say this is a battery, and here I have a switch, and this is a closing switch. This is a closing switch. This is what? This is a battery. This is a coil. Fine. So here it's a battery, a tapping switch is connected in series to the coil. And as the switch is closed, what happens? Current increases. Obviously, as you switch on your circuit, current will sooner increase, no? So current increases. So as the current increases, magnetic flux will also increase. So when the magnetic flux will increase, what will happen? From a zero to a certain value, it will increase. From zero to a maximum value, it will increase the current as well as the flux. So what happens? The direction, the induced current flows in opposite direction to the direction of this battery current. So this flows, the induced current flows in the opposite direction. Now let's take a similar case. This is your coil. This is your battery. Switch is here. Let's say this is opening switch. So now what will happen? See, as this tapping switch is opened, current and magnetic flux through the coil will decrease. It's like you're switching off the circuit. So whatever current was there at its maximum value, from the maximum value, current will sooner, and ultimately it will become zero. This is how just what happens in your normal, if you switch on a bulb. When you press the switch, you see the bulb glowing because current increases. When you switch it off, means the circuit somewhere gets broken, and that's why the bulb's luminous intensity, it decreases. So similarly, here is the case. From a maximum to a zero value, the what is happening to the current? It is decreasing. Similarly, flux is also decreasing. So what happens? When this decreases from a maximum value to zero, the induced current flows in the same direction as that of battery. Let's say if this was the direction of the current, so this is the direction. If this was the direction, here it becomes opposite. This becomes the direction of induced current. So this cannot come in your exam directly. How this can come? This portion, only these two figures, by just asking you in the theory papers, in those theoretical questions, like if a switch has been closed, what happens to the direction of induced current? Like this question can come from these two. Otherwise, usually questions, you know how they come. What is meant by self-induction? Define self-inductance. Just give its units, dimensions, like this. A full-fledged complete question comes. So self-induction's definition is this. This is one more if theoretical questions come. Now, if you look at these experiments, no, can anyone tell me what is the relation between flux and current? Directly proportional to each other, inversely proportional to each other, current and flux. Can anyone answer?
Directly proportional.
Directly proportional, yes, Arthur. Correct. See, current increased, flux increased, current decreased, so flux decreased. So what is happening? Whatever is happening to the current, that is happening to the flux. So flux is directly proportional to the current. Now what do? We remove the proportionality sign. How do we remove it? By putting a constant. So here the constant that we get is L, which is known as coefficient of self-induction, or this is also known as self-inductance. This will be used in your AC also, alternating current, self-inductance. Fine. So remember the formula of EMF that we had studied? According to the Faraday's laws of EMI. What was EMF? What was the formula of EMF? Using Faraday's laws of EMI.
Minus d phi by dt.
D phi over dt. So only Atif is revising, I think. EMF is minus d phi over dt. Yes, right. This was given by Lenz law, and this was rate of change of magnetic flux. Now let us put the value of it. Phi is what? Phi is right now what we have seen, it's Li. So L is a constant. L is a constant, no, that we have added. So this becomes what? Pi over d. So this is the formula of EMF now. So how can you define self-inductance? This can also come in exam. See, if current is what? Current is 1 ampere. Using this relation, phi is equal to Li. Then phi will obviously be equal to 1. If this is the case, then this will happen. So how can you define self-inductance? So you can define self-inductance of a coil is numerically equal to the magnetic flux. But when is this condition valid? When this condition is given. So this is when unit current flows. Unit uh, unit current flows through. So if numericals come, numericals will be different. Numericals will be based on the formula that we have done right now. And we'll do one more formula also. But if a complete theory question comes, so these points you have to mention along with this. One more thing is often asked. Units and dimensions are also asked of it. Dimensions are rarely asked because dimension is a part of your 11th standard. But it can happen that dimensions are also asked. So see, L is what? L is EMF divided by di over dt. L was E divided by di over dt if you interchange it. So what does it become? Volt divided by ampere per second. So this is known as 1 Henry. H. So you will be using this. This is the SI unit of self-inductance. This is very important. And the other thing is the dimension. See, dimension you can calculate using L is equal to phi by I. Phi, if you people are not remembering, you can use it dA divided by I. Like this, you can find out the dimensions of it. So I remember it, so I'm writing down it directly. But anyone who wants me to show these calculations, just let me know. I can show you this. So this is the dimension. Dimensions are also asked. More often, define 1 Henry can be asked. So how will you define 1 Henry? By this only. 1 Henry is what? One self-inductance of a coil. It is 1 Henry if induced EMF of 1 volt is set up when the current on it changes with the rate of 1 ampere per second. So this also you can define 1 Henry. So this is what is self-inductance. Write down all these points about self-inductance, and if a question will come, which will be a pure theoretical question, all these things will be asked. First, to write what is the definition of self-inductance, this formula to define self-inductance, and units. Till units it is very important. Note it down. We'll see 1 or 2 formulas and we'll begin with the questions. So self-inductance of a long solenoid. What was the magnetic field of a solenoid, class? All the students type in the chat box what was the formula of magnetic field of a solenoid. We have done this, no? In chapter number 4. What was the formula of magnetic field for a solenoid? Class. Hamza, Kulsum, Sara, respond. What was the magnetic field for a long solenoid? Atif, correct. Sneha, you also. See, you people do not remember the formula. Yes, Sara, right. B is equal to mu naught Ni. Why are you people forgetting all the formula? I have to take a viva of your formula then. See, magnetic field is P is equal to mu naught Ni in this formula. Fatima, do you remember what was small n from here? What was the small n? Fatima. Sneha, can you answer? Not only number of turns, Akifa. It is number of turns per unit length, not just number of turns. The small n is basically number of turns per unit length. Remember, that's why in case of toroid, we have it n divided by 2 pi r because that becomes the number of turns. Fine. So B is equal to mu naught Ni. Sarah, what was the formula of magnetic flux? Magnetic flux. BA cos theta, yes, right. BA or B dot. So magnetic flux was what? Magnetic flux was BA. Fine. Now let us put the value of this in this. So phi will become what? Mu naught Ni into A. This is the value of flux that is present. Now this is what this we have to find out magnetic flux that is linked with the entire solenoid. We have to find out magnetic flux linked with the entire solenoid. So this will be equal to what? This will be equal to magnetic flux which is linked with each turn. Flux linked with each turn into the number of turns present. That's why, no? If you know flux linked with this turn, and there are some more turns. So if you know about this, you can multiply for rest of it and get it. So this is number of turns. So flux linked with the entire solenoid we are calculating. Flux linked with the entire solenoid. This is D solenoid. So this will be what? This will be flux linked with each turn. What was that? That was mu naught Nia. And number of turns is what? From here you can see number of turns is what? Number of turns is small n multiplied by capital L. So this becomes what? This becomes n into L. So if you multiply, this gets mu naught n square Ia L. This is the formula of it. Also, right now we have studied that phi is equal to Li. So both of these are equal, just equate it. Li is equal to mu naught n square IAL. Current gets cancelled. L is equal to mu naught n square AL. This is the formula of inductance for a inductance means self-inductance. Also, if you want to write it in terms of number of length, number of turns. So L becomes mu naught n square A divided by L. This is number of turns. And this is number of turns per unit. Just note down this, then we'll do some questions on this. So from the formula also you can figure out things that on which factors self-inductance depends on. So self-inductance directly depends upon the number of turns that are present. It depends on the area of the cross section. It depends on the permeability. So if it comes, you can mention these three things. Send the answers of this question. This is a very direct formula based question. Number of turns is mentioned, current is mentioned, and inductance is mentioned. Only phi is unknown. See here, number of turns is what? N is given as 200. 4 into 10 to the power minus 7. Yes. How did you solve, Kulsum? Yes, Kulsum? Is anyone able to hear her?
No diff.
No, no. Kulsum, leave it, leave it. When you're speaking, no, I think your mic is not working. Yeah, I'll explain. Number of turns, phi is equal to, is directly proportional to I. Basically, phi is equal to Li, that we know. If this was for a single turn, for n number of turns, this will be what? This becomes n into phi. Number of turns get multiplied. So here so from here phi will be equal to Li divided by n. L is given as 20 into 10 to the power minus 3 Henry. Current is given as 4 into 10 to the power minus 3 amperes divided by number of turns as 200. So yes, the answer is right. It will be 4 into 10 to the power minus 7 wafers. Note down the solution. I'm giving you more questions. Yes, Atif, correct. Anyone else has an answer? Or should I discuss it? It says what if a rate of change of current of 4 ampere per second, it means di over dt is given as 4 ampere per second. This induces an emf of 20 millivolt. What is the self-inductance? So E is equal to minus L di over dt. Magnitude of L will be E divided by di over dt. EMF is 20 into 10 to the power minus 3. Di over dt is 4. So this becomes what? This becomes 5 into 10 to the power minus 3 Henry, which can also be written as, not E. Yes, 5 into 10 to the power minus 3. So this can also be written as 5 millihenry. Fine class. One last question I'm giving you. Whoever has not noted it, just note it down. Then we'll start with your derivations test. Class on next Thursday, not today. Today is what? Today is 11th, no? Yeah. So not on Tuesday, Tuesday 16th, at least on Thursday, try to give a test on EMI, this complete lesson. It's a very short lesson. See, only mutual induction is left. Mutual induction will get over by, it will get over in the next class. AC will also start in the next class. Mutual induction is a very small topic. Whatever you studied for self-induction, if two coils are there, that becomes mutual induction. Formula gets changed, everything gets changed in case of writing part. So that you have to keep in mind. That we'll do in first half an hour, 45 minutes or 1 hour in the next class. At least give a test of EMI on 18th. By this, what will happen? This whole chapter will be prepared. See, AC is also a short lesson. EM waves is also very short. And I think that Earth magnetism was left from the chapter 5. And we'll be over by your book 1. So we will have quick revision classes of all these from chapter 1 to chapter whatever EM waves put on to. So all these lessons. So before that, at least give the test on EMI. I hope nobody has issue on 18th. Just let me know, class. At least write yes or no in the chat box. Okay, fine. So Akifa, you can do one thing. Take the screenshot of the. When do you have to leave? At what time? Akifa? Okay, right now only you have to leave. Fine, Akifa. All no issues. But do appear for the test on Thursday, next Thursday. At least this lesson will be clear by that time. Yes, Kulsum Atif. Right answer. All right, class, let's discuss it. I think this was sufficient time given to all of you. So here what it is given, voltage is given as 12 volts, the resistance is given as 6 ohm, inductance is given as 10 Henry. Then it says through a switch drives a constant current through the circuit, the switch is suddenly opened. If it takes 1 milliseconds to open the switch, it means time is given as 1 milliseconds. 10 to the power minus 3 seconds. To open the switch, find the average induced EMF. In this formula, minus L di over dt, EMF is unknown, we have to find this. L we know, T we know. How can we find I? See, using this data, V is equal to IR. So I will be equal to what? V divided by R. That becomes 12 divided by 6, which is 2 amperes. Now just put it into the formula that you have. This becomes what? EMF will be, this is 10 Henry into current is 2, time is 10 to the power minus 3. You have 20,000. Fine, just note it down. Just text me done when you all have written it. So do one thing, note this down, take a 10 minutes break, then we'll start with the test. After 10 minutes exactly, I'll start with the test. Fatima, I've received your sheet. You've submitted it, no? All right. You can leave. Fine. You can leave. Others also hurry up. Second one is just for air. Dielectric is not mentioned, no? So it's just for a normal expression of energy for parallel plate capacitors. Yes, class, time is up. Quickly try to submit it.